may seem weird to think about seeing back in time, space researchers do it every day. The James Webb Space Telescope, JWST's magnificent images of our universe have made this year one to remember. These are images that allow us to observe faraway galaxies in their pre-13 billion year state. It's the ideal moment to take a step back and be grateful for both our first-class seat on the cosmic elevator and the ability these photos give us to travel across time. The early universe, star birth and death, galaxy mergers, and planetary atmospheres are all depicted in these images. The JWST scientific discoveries are beyond believable, and it keeps breaking barriers. But how did the James Webb Space Telescope enable us to observe the universe's very first galaxies? Which of its findings break the laws of physics, and have we discovered any signs of life elsewhere in the cosmos? Join us as we explore how the James Webb Space Telescope just discovered galaxies that defy modern physics. The speed of light is one of the most well-known rules of physics that govern our universe, and when we refer to light, we actually mean all of the electromagnetic spectrum's wavelengths, which move at a staggering 300,000 kilometers per second. Light moves so quickly that it seems to happen instantly in our daily lives. However, traveling anywhere in the galaxy still requires some time, even at incredible speeds. When you stare at the moon, you actually see it as it was at 1.3 seconds ago. Even though it's a very brief glimpse into the past, it is still the past. The only difference is that photons, light particles emitted from the sun's surface, take slightly longer, over 8 minutes, to reach Earth. The Milky Way galaxy, our galaxy, is more than 100,000 light-years across, and the lovely young stars visible in the Carina Nebula image from the JWST are located 7,500 light-years away. In other words, the historical period represented by this nebula is around 2,000 years earlier than the time when ancient Mesopotamia is supposed to have developed the first form of writing. We are constantly looking away from the Earth and towards the past at how things once were. Astronomers can utilize light as it has been observed across time to try to piece together the mystery of our universe. We can observe some light spectrums with space-based telescopes that are blocked by Earth's atmosphere. The ultraviolet, UV, and visible portions of the electromagnetic spectrum were used in the construction and optimization of the Hubble Space Telescope. The JWST, on the other hand, was built to work with a variety of infrared light, and this is a significant factor in why the JWST can go further into the past than Hubble. Gamma rays, radio waves, and all other wavelengths on the electromagnetic spectrum are all emitted by galaxies. All of them provide crucial details about the many mechanics operating in a galaxy. On July 12th, NASA released some of the James Webb Space Telescope's first breathtaking images and data to the general public. The 4 targets, each of which is made up of 3 photos plus a spectrum, beautifully capture the infrared world. President Joe Biden made a 4th image, a sharply focused, ultra-deep field view, public on the night of July the 11th during a live broadcast. This image showed an older universe than anything we have ever seen. The images and data show how James Webb has evolved into a useful research instrument, highlighting the telescope's great potential to advance science. The Stephens Quintet group of galaxies, the Southern Ring Nebula and the Carina Nebula, are depicted in the 3 photos. The 4th target is the spectrum of WASP 96b, a gas giant exoplanet. The Carina Nebula, one of the largest and brightest nebulae in the sky, is 7,600 light-years away from Earth. It contains Eta Carini, a fading supergiant star on the edge of a catastrophic explosion, as well as Trumpa 14, one of the newest known star formation clusters. Its diameter exceeds 300 light-years. The Carina Nebula is a large, active, and occasionally violent star nursery. The place is humming with activity, which is very wonderful. This stunning image from the Webb telescope of the cosmic cliff of the Carina Nebula provides new details about this massive stellar nursery. Additionally, we are now able to observe brand new stars for the first time that had previously been completely hidden from view. In contrast, the Southern Ring Nebula is only 2,000 light-years away from our planet. It is a planetary nebula, a rotating gas cloud of a dead star that is expanding. Unbearably hot and emitting powerful ultraviolet radiation, the dying white dwarf star in the nebula's center illuminates the gas surrounding it. Every one of its outer layers has been blown off. The newly discovered parts of the nebula are visible in the photos, along with the gas-formed shells. 5 galaxies known as Stephan's Quintet are 290 million light-years away from Earth, but seem impossibly close to one another. Due to their interactions, 3 of the galaxies have evolved into lengthy spiral-like formations, while the other 2 are engaged in a type of cosmic dance that will eventually lead to the collision of the quartet. The 5 stars in the group range in age from very young to quite old, representing hundreds of millions of years of cosmic history. Not every significant picture captured by the James Webb Space Telescope will, however, be visually pleasing. Some of them will be maps like the one NASA recently unveiled, which consists solely of lines, dots, and squiggles. The striking impact of Webb's view of galaxy clusters and the magnificent beauty of the Carina Nebula image are missing from that graph. The tiny map is intriguing in its own quiet way, though, as are the numerous other charts that the Webb telescope will produce over the next 20 years. These photographs will push our capacity to imagine the characteristics of worlds that are far outside of our solar system. Naturally, you must first be conscious of what you are viewing. A large gaseous exoplanet that resembles Jupiter is shown in the figure with extensive information on its atmosphere. WASP 96b travels around its Sun in approximately 3.5 days and is 1,150 light-years from Earth. The temperature inside it exceeds 1,000 degrees Fahrenheit, about 538 degrees Celsius. The only known cloudless planet, WASP 96b, has remained a mystery and a top area of interest for further study since its discovery in 2013. Webb's new observations have provided scientists with more knowledge about that unusual atmosphere. When Webb examined the starlight that reached the exoplanet's atmosphere, it was able to spot the telltale sign of water and even evidence of clouds. On this incredibly hot planet, clouds are quite unusual. Because rock is so heated, it can condense in the air like water does on Earth. But unlike Earth, sand makes up the clouds on WASP 96b. It became obvious that many other substances besides water will condense under the right pressure and temperature conditions. Exoplanets will no longer be viewed as enigmatic cosmic objects, but rather as very real locations with an alien sky thanks to the Webb telescope. There are an estimated 300 million planets in the Milky Way galaxy alone that may be habitable, and several of these planets are barely 30 light-years from Earth. In a sense, humanity's neighbors in the galaxy are these planets. The most distant confirmed galaxy prior to the James Webb Space Telescope's deployment was GNZ11, which astronomers observed when it was roughly 420 million years after the Big Bang, giving it what astronomers refer to as a redshift of 11.6. Redshift is a term used to express how much the universe has stretched the light coming from a galaxy. The further back in time we perceive a galaxy, the higher the redshift. We'll be able to observe incredibly far-off galaxies with the JWST as recently as 100 million years after the Big Bang, which took place some 13.8 billion years ago. Therefore, light from 13.7 billion years ago will be visible to us. However, the fact that those galaxies are not 13.7 billion light-years away is about to turn your head. That is because those galaxies are currently 46 billion light-years away from us. This mismatch, which makes operating on a very large scale difficult, is entirely due to the expanding cosmos. Dark energy is something that is causing the universe to expand. It is believed to be a universal constant that operates uniformly over all of space-time, the fabric of our universe. And the impact of dark energy on the expansion of the universe increases with its size. Because of this, the cosmos is actually about 93 billion light-years across, despite being 13.8 billion years old. On a galactic scale, we are unable to observe the impact of dark energy inside the Milky Way, but we can do so across much longer cosmological distances. A week after the first JWST science photos were made public, astronomers announced the discovery of galaxies at redshift 13, or roughly 300 million years after the Big Bang. The record is currently being broken by a new wave of scientific discoveries, with some astronomers reporting the discoveries of galaxies up to a redshift of 20. If this is the case, then we are witnessing these galaxies in their pre-Big Bang state. That's a big if, because none of these redshift estimates have been verified as of yet. It will take spectroscopic study, which divides an object's light into a spectrum, to verify the distances of these galaxies. The analysis will be presented later, but it is apparent that JWST is completely able to find galaxies from this long-gone age. JO723's gravitational lens helped astronomers led by Haojing Yan of the University of Missouri Columbia find 88 candidate galaxies beyond a redshift of 11, including a few that are thought to be a redshift of 20. These galaxies would be the furthest ones ever discovered if confirmed. In two other studies, high redshift galaxies are discovered in regions of the sky where JWST has only made deep exposures without using gravitational lensing. These photos are a part of the Cosmic Evolution Early Release Science (SEERS) survey, which was taken by JWST's near-infrared camera on photographs of 10 distinct areas of the sky. 6 of these patches are observed by JWST's near-infrared spectrograph NIRSpec, while the mid-infrared instrument MIRI focuses on 4 of them. Callum Donnan, a PhD candidate at the University of Edinburgh, led a team of astronomers that discovered a candidate galaxy at a redshift of 16.7, or only 250 million years after the Big Bang. The team also discovered 5 more galaxies, all of which have redshifts larger than 12, breaking the previous record for redshift set by the Hubble Space Telescope, the JWST's predecessor and current collaborator. Another team, led by Stephen Finkelstein of the University of Texas in Austin, discovered a galaxy using the same observations from SEERS that has a redshift of 14.3, placing it 280 million years after the Big Bang. The researchers have named this galaxy Mais's Galaxy in honor of Finkelstein's daughter. The astronomers discovered that the Hubble Space Telescope may have also observed this galaxy, although it was not known about at the time. If a closer examination of the archived data does really identify the galaxy, Mais's Galaxy must have emitted extremely intense ultraviolet radiation as a result of a significant burst of star creation for the Hubble to have discovered it. In fact, all of the possible distant galaxies show evidence of significant ultraviolet light emission, which may be sufficient to resolve the question of what ionized the hydrogen gas in the cosmos and to end the so-called cosmic dark ages. Astronomers have proposed a variety of explanations throughout the years, from radiation from the earliest stars and galaxies to the first supermassive black holes' radiation outflows. The galaxy ultraviolet luminosity function between redshifts of 8 and 15 is calculated by Donnan's team in their publication. The amount of ultraviolet light emitted by galaxies at any given time is averaged out using this function. Because a galaxy emits more ultraviolet light when more hot, young stars are forming there. The value is closely related to star formation. According to Donnan's team, the stars in these early galaxies release more than enough ultraviolet radiation to ionize the universe. These newly discovered high redshift galaxies can be viewed as cosmic newborns. In contrast to current galaxies, which can house hundreds of billions of stars, these galaxies are merely a few thousand light-years across and only contain tens of millions of stars. The cosmic babies, according to astronomers, could be as young as 20 million years old and are thought to be less than 100 million years old. The very first galaxies in the universe, which might be located at redshift 25 or beyond, have not yet been discovered by scientists. However, the newly discovered galaxies reflect generations of galaxies that came just after and are still in their infancy, according to experts. The abundance of high redshift galaxies that JWST is discovering so early in its mission, along with the amount of ultraviolet light redshifted into the longer wavelengths of infrared, making it visible to JWST, suggests that galaxies were numerous in the early history of the universe. In contrast to certain predictions, there may be a steady fall in star formation as we look further back in time, as opposed to a sudden decline after redshift 11. Should follow-up spectroscopy validate these redshifts, it means that our universe was already aglow with galaxies less than 300 million years after the Big Bang, Finkelstein's team wrote in their paper. Now that JWST has discovered these strong galaxy candidates at great distances, the following questions how far back in time JWST can see and whether it will be sufficient to find the very first galaxies that existed, perhaps just 100 million years after the Big Bang. The Webb mission will strengthen that effort by revealing hitherto unknown features of previously studied targets, opening up hitherto inaccessible worlds, and possibly even spotting compounds that are known to be indicative of the existence of life. So how does it work? The James Webb Telescope concentrates on a star system and waits, soaking up the incoming light in order to analyze the exoplanet atmosphere. The star's face is briefly obscured by a planet that enters our range of vision and moves across it. However, some light does escape the planet and travels through the atmosphere on its way out. As the light approaches the Webb telescope, it carries the chemical signatures of any gases that might be present in those cloud tops. The telescope's detectors scatter the light in a manner similar to how a glass prism divides sunlight into rainbow hues. Then they plot them all on a chart known as a spectrum. Astronomers carefully examine such data, searching for indications of well-known chemicals and compounds. But how about the indication of life? Water vapor is present as seen by the peaks in the WASP-96b spectrum. In some situations, it helps to be an expert astronomer to spot the indicators of clouds and haze. However, finding another Earth-like planet may be more difficult than you expect, as assessing whether a planet is livable is not an easy task. About 40 light-years away is a magnificent star system. 5 years ago, NASA revealed that it and many collaborators had discovered numerous Earth-sized planets orbiting a single star within its habitable zone. The TRAPPIST-1 system became well known around the world because of this discovery. Astronomers have since been keen to learn more about these nearby worlds that potentially mimic Earth. One of the James Webb Space Telescope's initial research cycles will focus on researching the TRAPPIST-1 system. Long-term, the research will lay the groundwork for the hunt for biosignatures that might reveal the presence of life on any of the planets in the TRAPPIST-1 system. It will be investigating to see if the planets in the TRAPPIST-1 system have atmospheres. But understanding planets that are different from our own poses a number of challenges. Recent modeling work shows that in addition to a planet's distance from its star and its composition, a planet's potential habitability is strongly influenced by the distribution of land throughout its surface. Researchers are modeling Proxima Centauri b, an exoplanet the size of Earth. Similar to TRAPPIST-1, Proxima Centauri is a red dwarf star. These stars are smaller and cooler than our Sun, so the planets can orbit them quite closely and still be in the habitable zone. Similar to TRAPPIST worlds, Proxima Centauri b is tidally locked. The planet is therefore symmetrical, with one side constantly facing the star and the other constantly pointing into space. Our solar system does not have any planets that display this behavior, although exoplanets commonly do. The idea that Mercury was tidally locked was frequently held, although the truth was far different. On the other hand, the moon on our planet is shaped similarly, with one side always facing us and the dark side always facing away. Tidal locking of exoplanets may affect their habitability, since astronomers expect that one side of the planet will be much hotter than the other. However, this might be mitigated by an atmosphere with winds that spread heat over the planet and make it more hospitable for life. The day side of the planet is always in the light since it faces the star, while the night side is always in the dark. The model showed that on planets with more land, there was less rain, more heat, and a larger temperature difference between day and night. There was more precipitation and cloud cover on planets with larger ocean basins. Because ocean water might periodically freeze into ice, the volume of liquid ocean had an effect on the amount of water in the climate and the temperature on the planet. The distribution of the land might alter the average surface temperature of a tidally locked planet by up to 20 degrees Celsius, the researchers found, even if the total amount of land remained constant. It is challenging to establish how much of an exoplanet is land and how much is ocean by examining spectra like those James Webb will get when applying this theoretical research to actual data on exoplanets. Learning more about these exoplanets will be a truly thrilling experience. Don't begin preparing to move to Earth 2 just yet, though. It won't be simple to find a habitable planet from billions of kilometers away. This early data, however, shows that the James Webb Telescope is capable of identifying minute chemical fingerprints in exoplanet light. Astronomers will utilize the JWST to discover elements like oxygen, methane, and carbon dioxide that are more intriguing to study than water, or even better, more than one element in the same atmosphere. However, because Webb was not designed to search for extraterrestrial life, the telescope can only closely analyze a few of the closest potentially habitable worlds. Additionally, it is restricted to monitoring changes in atmospheric levels of methane, carbon dioxide, and water vapor. Even while some mixes of these gases may be suggestive of life, Webb is unable to detect the presence of unbonded oxygen, which is the strongest indicator of life. As soon as the intriguing event is discovered by the Space Telescope alone, astronomers must identify its precise origin. But until the next significant space telescope comes, Webb will educate us about the variety of extraterrestrial atmospheres in the cosmos. Over a quarter of the first year's observations with the telescope will be devoted to exoplanet research. Astronomers can search for various additional kinds of atmospheric gases as well as unusual clouds. They can even make assumptions about what might be buried beneath the clouds and predict the surfaces of extraterrestrial life using the data. By creating hypotheses about how and when these planets formed, we might learn more about the worlds beyond us, especially small rocky planets like Earth that orbit at the ideal, cozy distance from their star and maybe habitable worlds. A cutting-edge concept for future, even more potent space telescopes includes ideas to block the glaring brightness of a planet's host star in order to expose starlight reflected back from the planet. This concept is akin to blocking sunlight with your hand to see farther away objects more clearly. Small interior masks or big exterior umbrella-shaped spacecraft could be used in future space telescopes to accomplish this. Studying light reflecting off a planet is significantly simpler after the starlight is obstructed. Methane is a gas that is released by both cows and volcanoes. Sadly, the majority of gases produced by terrestrial life can also be produced by non-biological causes. In addition to converting water molecules into oxygen and hydrogen through photosynthesis, sunlight also does this. Astronomers are likely to come across some false positives when looking for extraterrestrial life. In order to help rule out false positives, astronomers must have a detailed grasp of a planet of interest to evaluate whether its geologic or atmospheric processes could resemble a biosignature. The next generation of exoplanet research might be able to produce the impressive proof necessary to prove the existence of life. The initial data from the James Webb Space Telescope gives us a glimpse of the enormous developments to come. A bold new era is just getting started in the field of space science. We weren't even aware that there were galaxies outside of our own until just a century ago. And now that we know there are trillions, we have an abundance of options. The JWST will continue to lead us on weekly excursions through space and time for the foreseeable future. Let us know what you think in the comments section below.